Hello and welcome to Data Science for Everyone. Today I'll be guiding you through this course on handling dates and times in Python. Let's get started. Python includes a special class for working with dates called date. It's similar to other data types like strings, numbers, or arrays. To start working with dates, we first need to import the date class. All date and time related classes live inside Python's DateTime module. We create a date using the date function. Let's create two dates by calling the date function. The date function takes three arguments: year, month, and day in that order. We have created two dates, March 12, 2025 and May 11, 2025. Later on, we'll see how to convert strings into dates, but for now, we'll stick to creating them manually or using pre-made lists. Once we have a date object, we can easily get its individual parts. To get the year, we call the .year attribute. For month or day, we can call the .month and .day attributes respectively. It's pretty straightforward and easy to remember. To find out what day of the week a date falls on, we can use the .weekday method. This method returns a number from 0 to 6, where 0 is Monday, 1 is Tuesday, and so on, up to 6, which is a Sunday. Let's explore how to do math with dates. That means things like figuring out how many days are between two dates, moving a date forward or backward, and comparing which date comes first. If we pick two numbers, let's say 21 and 24, we can use Python to figure out which one is smaller. We'll store them as variables and place them in a list. Then we use the min function and Python will return the smallest one. In this case, that's 21. We can perform other mathematical operations on numbers as well. Now let's switch from numbers to dates. We'll use the date class from Python's DateTime module. We create two date objects. We can then put this into a list and use the max function again. If we call the max function, we get the latest date. In this case, it is May 11, 2025. Just like numbers, we can subtract one date from another. If we subtract dates, Python gives us a new type of object called a Timedelta object. This object tells us the difference between two dates. If we check its .days attribute, we'll see how many days are in between. In this case, 60 days. We can also add days to a date. To do that, we import Timedelta. Then, for example, we can create a 10-day time span. If we add that to March 12th, Python gives us March 22nd. Python makes it easy to turn date objects into strings that are easier to read or use. This is helpful when we want to display a date on the screen, include it in a file name, or save it in a CSV or an Excel file. Let's start with how Python shows a date by default. We'll import date from DateTime and create a date for March 12, 2025. When we print this date, Python shows it like 2025-3-12. That's year first, then month, then day, all separated by dashes. This format is known as ISO 8601 format. It's standardized and always uses two digits for month and day, even if they're below 10. If we want to get this date as a string, say to save it in a CSV file, we can use the ISO format method as shown here. One big advantage of ISO 8601 format is that it sorts dates properly when they are in string format. Let's say we have two dates as strings. If we put them in a list and sort it, they'll be ordered from oldest to newest. That's because ISO 8601 format puts the biggest unit, which is year, first, followed by month and day. This makes it really useful for naming files in a way that keeps them in chronological order. If we don't want to use the ISO format, Python gives us other options as well. We can use the strftime method to format dates however we want. Let's take a look at some examples. The strftime method lets us create a string version of a date using a format code. Let's create a date for December 3rd, 2025. If we use strftime %y, Python gives us just the year. There are more format codes as well. %m gives us the month as a number, and %d gives us the day, and so on. We can combine these in any way we like to match the format we need. So far we have been working with dates. Now it's time to bring in the concept of time, not just the day, but the hour, minute, and second within that day. Let's look at an example. Imagine something happened on March 14th, 2025 at 2:10 p.m. Instead of just storing the date, we want to include the exact time. Let's see how we can represent this in Python. To work with both dates and times, we need to import the DateTime class from the DateTime module. Let's make a new DateTime object and store it in a variable called dt. The first three values we pass in are the same as when we create a date object. The year followed by the month and then the day, all as numbers. After the day, we add the hour. Python uses 24-hour time format by default, so 2 p.m. would be 14. Next, we enter the minutes. In this case, it's 10. Finally, we include the seconds. So for 10 seconds past the minute, we add 10 as the last argument. Our full date time now includes all 6 parts: year, month, day, hour, minute, and second. If we need more precision, we can add microseconds. For example, we can add 0.25 seconds by adding 250,000 microseconds. Python can track down to millions of a second. And if we need even more precision, like nanoseconds, we'll cover that when we get to Pandas. That's a lot to remember. So if it helps, we can use named arguments as shown here. This makes the code easier to read and reduces the chances of mistakes. We can also take an existing date time and tweak it using the replace method. For example, here we're replacing the minute and microsecond. This gives us the new updated date time with the other values unchanged. Just like dates, date times can be displayed in many different ways. Python can also take a string and turn it into a date time. Let's first look at how to format and print a date time, then we can move on to see how Python can read one from a string. We'll start by creating a date time for March 14th, 2025 at 3:45 p.m. To turn this into a nicely formatted string, we'll use the strftime method. We'll print just the date using %y for the full year, %m for the month, and %d for that day. Next, we'll include time using %h for hour in 24-hour format, %month for minutes, and %s for seconds. We can also use codes for 12-hour time and add AM or PM instead if needed. To convert the date time to a 12-hour format with AM or PM, we can use the format codes %I for the hour and %p for AM or PM as shown here. Now let's turn a string into a date time. This is useful when we get dates from text files, websites, or APIs. To start, import the DateTime class from the DateTime module. The function we'll use is called strftime, which means string parse time. It takes 2 arguments, the string that contains the date time and a format string that tells Python how to read it. Let's say we have a string 10/12/2025 08:45:27. That's October 12, 2025 at 8:45:27 a.m. in the morning. Now we give Python the format it needs to understand the string. In this case, the format will be %month/%d and so on. This tells Python to expect a month, day, and year with slashes, followed by time separated by colons. If we check the type of the result, it's a DateTime object. And if we print it, Python shows a DateTime formatted version of the input text, proving that it was parsed correctly. The format must exactly match the string. Here we have incorrectly formatted the date by replacing the slashes with dashes. As you can see, there was an error while parsing the date time. Another common way to store date times is with Unix timestamps. These are just numbers counting seconds since January 1st, 1970, the start of time for most modern systems. To convert a Unix timestamp to a date time, we can use the from timestamp method. This gives us a readable date time. DateTime objects support arithmetic operations similar to dates. We can compare, add, or subtract time intervals from them. Since they include both dates and times, handling durations involves a bit more detail, but it's straightforward once you understand the basics. Let's take a look at an example. Let's assign the starting and ending times to variables named start_datetime and end_datetime. When we subtract start from end, we get a Timedelta object, which measures the length of time that passed between the two. By calling the total_seconds method on the Timedelta object, we can find out exactly how many seconds passed, as we can see here. We can also create Timedelta objects from scratch by importing it from the DateTime module. We can just specify the amount of time we want, like 2 seconds or 8 minutes as shown in the code. We can use the Timedelta object to modify any DateTime objects as shown here. We can make time deltas of any size, days, hours, or even weeks. For example, here D3 is a duration of 8 days and 9 seconds. Time deltas can also represent negative durations. Here, delta 4 equals -2 days, and adding it to the start actually moves the date time 2 days into the past. Sometimes we need to know the exact moment something happened. Until now, the DateTime objects we have seen are naive, meaning they don't include any information about their time zone. Because of this, we can't accurately compare times from different parts of the world. Let's see how we can add time zones to our date times. The first standard time reference is called UTC, or Coordinated Universal Time. Clocks worldwide are set based on UTC. Clocks to the west of UK are behind UTC, and those to the east are ahead. Let's demonstrate time zones. We'll import DateTime, Timedelta, and timezone first. The timezone module lets us specify the time zone of our DateTime objects, so they become aware of their offset from UTC. Suppose we take a car ride that started at 4 p.m. in New York, which is UTC -4. We create a timezone object for UTC -4 and then attach it to our DateTime. When printed, this DateTime now shows the UTC offset. Being time zone aware means we can convert times easily. For example, to see what the car ride time would be in Tokyo, we create a Tokyo time zone object which is UTC +9 and use the asTimeZone method. Now the time adjusts to show the same moment, but according to Tokyo's clock. There is a key difference between changing the time zone with asTimeZone method and just swapping the time zone info directly with the replace method. Using replace only swaps the time zone label without adjusting the clock time, but the asTimeZone method changes both the time and the offset, so the moment stays correct globally. Now that we know how UTC offsets work, let's move on to using the time zones in real situations. There's a database called TZ that's updated several times whenever the time zones rule change. Many programming languages use this database. Because time zones change often, it's better not to hard code them into softwares. Instead, we can use a package called dateutil that taps into this database. Let's create a time zone object for the Pacific time zone in the United States. The TZ database organizes time zones by continent and then by a major city. For example, America/Los Angeles is used for US West Coast. We can get this time zone by calling the getTZ method with the argument set to America/Los Angeles. Here are some other examples. Let's look at the start date time again. Instead of manually adding the UTC offset, we apply the timezone object from TZ. When we check the result, we'll see that it automatically includes the correct UTC offset. The best part is this timezone object updates the UTC offset depending on the date and time. For example, if we create date time for a ride in winter versus summer with the same time zone, the offset changes accordingly. We'll cover daylight saving time soon, but basically clocks shift twice a year in some regions. Instead of manually tracking these changes, TZ handles it for us. It even knows historical changes going back decades. If we have data across many years, using TZ helps us keep all our timestamps consistent. Some regions adjust their clocks twice a year to enjoy longer evenings in summer. This adjustment is known as daylight saving time, though a better name might be daylight shifting. In some countries, it's called summertime. Let's look at some examples for daylight saving time. We create two DateTime objects for March 12, 2023, one at 2:59:59 am and the other at 3 am, both without the time zone info. Printing their ISO format confirms their times. Subtracting them shows a difference of 1 hour and 1 second, matching the clock change. Notice that these times are not time zone aware. Let's make these times time zone aware. To handle time zone aware DateTime objects, we first define the time zones manually. We create an Eastern Standard Time object with a UTC offset of -5 hours and an Eastern Daylight Saving Time object with a UTC offset of -4 hours. Then we apply these time zones using the replace method. Now when subtracting these time zones aware DateTime objects, the difference correctly shows only 1 second, since the hour was skipped due to daylight savings adjustment. To identify the exact moment clocks change for daylight saving time, the dateutil library is highly effective. Instead of manually defining time zones, use dateutil's getTZ method to create a time zone object for America/New York. In this demonstration, create time zone aware DateTime objects just before and after the daylight saving time transition at 1:59:59 am on March 12, 2023. Dateutil automatically assigns the correct offsets, recognizing the daylight saving change from UTC -5, which is UST, before the transition to UTC -4, which is EDT after. This shows how time zone offsets change automatically when crossing the DST or the daylight saving time boundary. Now let's see how we can use our knowledge of DateTime in Python on datasets. We'll be using data from a scooter sharing service in Austin, Texas, where each record shows when a scooter was unlocked and when it was returned. Each trip has a start and end date time, perfect for practicing with the date and time data. Let's begin by importing Pandas as PD. I have made a detailed video on Pandas on this channel, and if you want to learn data analysis using Pandas, do check it out. We'll first load the CSV file named scootersharingdata.csv using Pandas read CSV method. The data is saved into a variable called scooter. To get a quick look, we'll print out the first 3 rows using the head method. You'll notice that index starts at 0 on the far left. Each row contains fields like start time, end time, start location, end location, and the distance traveled. The link to this data is in the description below. To pick a specific column like start time, we use brackets. For a single row, we can use iloc. For example, iloc3 gives us the 3rd row. Currently, these start and end time columns are stored as plain text, not as real datetime objects, which limits what we can do with them. We can instruct Pandas to parse certain columns as datetime during loading by adding the parse_dates argument to read CSV method. We pass in a list of column names we want to be converted, in this case the start time and the end time. This way Pandas automatically detects and converts them to datetime objects. If that fails, we can use the toDateTime method and specify the format manually. After loading with parse_dates, accessing the start_time for a row returns a Pandas timestamp. This object behaves much like a Python datetime, letting us manipulate and analyze dates easily. Now that start and end times are datetime objects, we can subtract them to find the right duration. Here we are creating a new column called duration by subtracting start time from end time. The result is a datetime object showing how long each ride lasted. Printing the first 5 rows shows the durations. Pandas supports chaining methods for cleaner code. For example, to convert durations into total seconds, we can use the .totalSeconds method. Viewing this converted value shows ride lengths in seconds instead of time deltas. We can also summarize time data using built-in methods like .sum or .mean as shown here. Now let's generate some plots. We'll be using the Seaborn plotting library to make our plots. I have made detailed tutorials on plotting libraries like matplotlib and Seaborn on this channel. I have them linked in the video description. This plot shows how trip durations vary depending on the time of day. We can see whether users tend to take longer trips or shorter trips during certain hours. For example, longer trips occur during midday when users have more time, while shorter trips are more common during commute hours. Here's a box plot where we are looking at how far users travel on different days. The box plot shows the distribution of trip distances with the median along with variations. This helps us see patterns. Here, for example, we can see that travel distance on Sundays were longer on average compared to other days. With that, we have come to an end of today's video on datetime analysis in Python. Please make sure to hit the like and subscribe button. Also, check out my other videos on Pandas, Matplotlib, and Seaborn. Thank you.